In the early 1950s, intercontinental flight schedules were essentially dictated by the weather. High-altitude currents meant nature decided exactly when you arrived. The geography of the Atlantic created a paradox for travelers. Flying eastbound to Europe was assisted by the jet stream, but the westbound trip meant colliding with a massive wall of prevailing headwinds that slowed aircraft to a crawl. Existing aircraft like the DC-6B and the standard DC-7 lacked the range to overcome this resistance. To make it to New York from London, they had to land and refuel in Gander or Iceland, rendering the route far less profitable. Airlines demanded a solution, a machine that could cross the Atlantic non-stop in both directions while carrying a full payload of passengers and cargo. Douglas Aircraft's response was the DC-7C, an aircraft specifically marketed as the 7Cs. Solving the headwind problem required mechanical intensity that had never been asked of a commercial airliner. To bridge the final gap in the map, engineers had to push piston technology into a new realm of complexity. By splitting the wing root of the standard DC-7 and inserting 5-foot sections, engineers expanded the wingspan to over 127 feet. This created volume for a 7,824-gallon fuel capacity and moved the engines further from the cabin, reducing noise and vibration for passengers. Powering this heavier frame was the Wright R-3350 Turbo-Compound, a complex twin-row 18-cylinder radial engine. The secret to its power lay in 3 power recovery turbines. Sitting in the exhaust path, they captured high-velocity waste gases, feeding that energy back into the engine's crankshaft through fluid couplings. This thermodynamics trick provided a 20% boost in power, allowing the R-3350 to generate a massive 3,400 horsepower during takeoff. This engineering allowed the DC-7C to fly longer distances than any piston airliner before it, but it resulted in a high-strung, overstressed machine that operated at the very limits of its mechanical endurance. With the Atlantic route solved, the industry turned toward the ultimate geographic barrier of the 1950s, the North Pole. Polar flying was functionally impossible at the time. Magnetic compasses became useless near the pole, and traditional star-based navigation was impossible during the months of total Arctic darkness. Scandinavian Airlines System, or SAS, intended to use the extreme range of the DC-7C to open a direct polar route connecting Europe to Tokyo. Their solution was a high-precision Bendix gyro compass that maintained its heading regardless of magnetic interference. Navigators used this in tandem with the Greenwich grid, a rigid coordinate system that allowed them to plot a straight line over the top of the world. To find the sun when it was hidden below, SAS was utilizing these technologies to run the first regular trans-Arctic services to Los Angeles and Tokyo, while Pan Am began reliable non-stop crossings of the North Atlantic. The DC-7C had effectively completed the map of global commercial aviation, reaching the final destinations that were previously inaccessible to non-stop flight. But pushing the limits of the reciprocating engine came with a systemic cost in reliability. The Wright R-3350 was a maintenance nightmare. The engines were prone to severe overheating, chronic oil leaks, and frequent failures within the power recovery turbines. To prevent the engines from destroying themselves in flight, flight engineers had to obsessively monitor individual cylinder head temperatures across a dense wall of cockpit dials. For the airlines, the immense ground time and specialized labor required to keep the DC-7C airworthy began to weigh heavily against its commercial success. Ultimately, the DC-7C wasn't defeated by the geography it set out to conquer, but by the mechanical friction of its own design. In October 1958, the DC-7C had been in service for only 28 months when the first commercial jetliners began non-stop service across the North Atlantic. The arrival of the Boeing 707 and the Douglas DC-8 marked a sharp technological fracture in the industry. These new jet engines were vastly more reliable, operated with fewer moving parts, and allowed aircraft to cruise smoothly at 36,000 feet, far above the weather systems that challenged the piston fleet. The most capable piston airliner ever built was sidelined almost overnight. Within a few short years, the 7Cs was largely relegated to cargo hauling and secondary charter work. The DC-7C stands as the final evolution of the long-range propeller era. It was the machine that successfully bridged the final gaps in global navigation, serving as the ultimate solution for intercontinental travel until the first jets arrived to do the same job with far greater efficiency.